My name is Boris Galkin, presenting the work Intelligent Base Station Association for UAV Cellular Users, a Supervised Learning Approach. In recent years, unmanned aerial vehicles, or UAVs, have become increasingly popular in a variety of applications, including package delivery, surveillance and security, as well as emergency applications. All of these applications require the UAVs to maintain a wireless connection back to its operator or to a controlling server. The emerging 5G cellular network is intended as a candidate for providing this wireless connectivity. While prior generations of cellular networks were intended for ground user use, the 5G cellular network is intended to accommodate a variety of new types of users, including UAVs. Experimental measurements carried out by the wireless community have shown that UAV users experience unique connectivity challenges when attempting to connect to existing cellular networks. First of all, this is caused by the interference received by the UAVs when they are in the air. As UAVs fly above buildings in a typical urban environment, they are able to have unobstructed line of sight channels on base stations that are potentially kilometers away. As a result, the UAVs receive very strong interference power signals from these distant base stations when compared to the performance of typical ground users. Another issue is related to the antenna misalignment of UAV users. Typical macro base stations positioned on building rooftops have antennas which are tilted towards the ground. That is where the typical ground users of cellular networks are located. Of course, UAV users, when they are in the air, will, as a result of this, receive side lobe signals from base stations instead of the main lobe signals that typical terrestrial users receive. A result of this is that in some situations, UAV may receive a stronger signal from a base station which is further away than a closer base station. As a result of these unique radio conditions in the sky, a UAV user does not perceive the cellular network as a set of discretely separated coverage cells. A UAV is able to connect to a number of base stations around it because of the strong received signal power. Therefore, to maximize the received service quality for the UAV user, it should be able to intelligently connect to the most appropriate base station as observed from its position in the sky. When operating in the sky, a UAV can make observations about its surrounding radio channel conditions and has access to information about its surrounding environment, which it can use to make intelligent decisions about base station connectivity. In this paper, we propose using a neural network which is trained to take in this environmental information and to decide which base station a UAV which is equipped with a directional antenna should connect to and should align its directional antenna towards to maximize its received service quality. We consider a UAV positioned at a height gamma above ground in an urban environment. The UAV is equipped with a directional antenna of beam width omega. The UAV points this directional antenna towards its associated base station, which results in the antenna illuminating a ring sector area of shape W on the ground. In this case, the UAV has associated with the base station at location X1, and the base station at location X2 is inside of this illuminated area W. As a result of being inside of area W, the base station at X2 generates interference for the UAV. Any base stations that fall outside of the area W are assumed not to cause any interference due to the very low side lobe antenna gain of the UAV directional antenna. The base stations are distributed according to a homogeneous Poisson point pattern. Each base station has an antenna array with NT antenna elements, which results in the antenna gain of the base station being as given in the equation as a function of the vertical angle between the UAV and the base station. In addition to its directional antenna, the UAV is equipped with an omnidirectional antenna used for channel sensing. By being omnidirectional, this antenna allows the UAV to receive signals from base stations all around it, irrespective of where the directional antenna may be pointed. The buildings in the environment are capable of blocking line of sight between the base stations and the UAV, which will attenuate the received signal. We model the buildings according to a square grid, with each building having a random height which is distributed according to a Rayleigh distribution. When the UAV aligns its directional antenna with its associated base stations, the signal to interference and noise ratio of the channel is given as in the equation, where P is the transmit power of the base station, H is the multipath fading, eta and mu are the antenna gains of the UAV and the base station antennas respectively, C is near field path loss, alpha is the path loss exponent, L and IN are the aggregate interference power from the base stations which have line of sight and non-line of sight on the UAV, and sigma squared is the noise power. Using its omnidirectional antenna, the UAV measures the received signal power of the nearby base stations. We assume the UAV also has a map of nearby base stations available to it, which tell it the distances of those base stations to the UAV. It passes this information to a neural network, which then makes a decision which base station the UAV should associate with, which will give it the best SINR through its directional antenna. This is a classification problem where a neural network is presented with environmental information and needs to pick from one of several discrete options. In this case, these options represent zeta candidate base stations from which the neural network needs to pick the one it believes will give the best directional antenna SINR. The neural network inputs are the UAV height, a vector P of the received signal powers of the candidate base stations, a vector R of the horizontal distances of the candidate base stations to the UAV, and a zeta by Xe matrix F of the horizontal distances of base stations, which will cause interference for the UAV if it were to align its antenna towards each of the candidate base stations. We use a feed-forward neural network with an input layer, two hidden dense layers, and an output layer. The number of neurons in the input and output layers correspond to a zeta value of 10 and a Xe value of 20. This neural network is trained over 200 epochs using the Adamax optimizer. The data set that we provide to the neural network for training is generated via simulations. The neural network needs to be trained using labeled data. We simulate the UAV generating a dataset of this data by taking measurements in an urban environment. The UAV hovers at a location, records the environmental information P, R, and F, and then iteratively aligns its directional antenna with each of the zeta candidate base stations. It observes the signal to interference and noise ratio of the channel for each of those base stations through its directional antenna, determines which base station has the highest SINR, and then records the index of that base station as the label to go with the associated data that it measured. To evaluate the performance of our neural network association policy, we compared against heuristic non-neural network-based association schemes. As the UAV has access to information about its surrounding environment, it can use that information directly to make an association decision. The omnidirectional antenna on the UAV allows it to measure the signal to interference and noise ratios of the channels from the base stations to the UAV omnidirectional antenna, and it could choose to associate based on that. The UAV also has information about the base station distances to it, which means it can choose to connect to the base station that is closest to it without taking into account the received signal powers. In this figure, we show how the height of a UAV above ground will affect its coverage probability. That is, the probability that the signal to interference and noise ratio of the directional antenna link between the UAV and the base station it's associated with will be above a certain minimum threshold. We can see that at very low heights above ground, all three association policies are able to give a very high coverage probability. This is because of the fact that when the UAV is close to the ground, it experiences very little interference from base stations, as those base stations are blocked by the buildings around the UAV, which reduces the signal power of the interference. As the height above ground of the UAV increases, the coverage probability begins to drop. This happens because the interference power received by the UAV increases as more and more line of sight channels appear, and also because base station antenna misalignment starts becoming a bigger and bigger issue due to the UAVs being above the base stations and receiving side lobe signals. At very large heights, the SINR association policy gives very poor performance. This is because the highest SINR measured by the omnidirectional antenna of the UAV appears to come from base stations which are going to be far away from the UAV due to the aforementioned antenna down tilt on the base stations. As such, when the UAV points its directional antenna towards one of these distant base stations, it will illuminate a very large area, which will increase the amount of interference that the UAV is able to receive on the channel. By comparison, if the UAV chooses to associate to the closest base station, then it will get a relatively good performance. This is because the antenna on the UAV will be tilted at a steep angle down towards that base station, which will reduce the amount of interference received by the UAV, even though the base station will be misaligned with the UAV and the UAV will be receiving a weak side lobe signal from the base station. This lack of interference will result in a higher coverage probability. The neural network noticeably outperforms the two heuristic schemes across all heights. At low heights, the neural network knows that it can avoid interference due to the presence of buildings, and therefore it should associate to the base station that gives the strongest received signal as observed by the omnidirectional antenna. Whereas at very large heights, the neural network is aware of the significant presence of interference and therefore prioritizes connecting to base stations which are closer to it to tilt its antenna down at a steeper angle and reduce the received interference power. The biggest performance improvement is found in the middle range of heights. At these heights, the UAV is high up enough above ground that it receives weak side lobe signals from the base stations, but at the same time it is not so high up that it can tilt its own antenna down enough to minimize received interference. The neural network is able to successfully weigh the multiple factors affecting the choice of the base station to associate with to pick the best one. Here we show the effect of the base station density on the performance of the three association schemes. When the density of the base stations is low, the choice of a suitable base station becomes relatively easy, as there is a lack of interference in the environment and the UAV simply needs to pick the base station with the best received signal power. As the density of base station increases, the performance gap between the neural network and the two heuristic schemes widens. As the density increases, the environment becomes more and more complicated, which means that the intelligence of the neural network is able to benefit the UAV more and more. As the beam width of the UAV directional antenna is increased, the coverage probability drops due to the increasing amount of interference received by the UAV. As the UAV beam width increases, the performance improvement of the neural network becomes less and less noticeable, as the intelligence of the neural network becomes insufficient for mitigating the interference received by the UAV antenna. In this figure, we show the probability that the neural network will pick a given base station for the UAV to connect to as a function of the UAV height above ground. We can see that the neural network will select the closest base station approximately half the time. It does not choose the closest base station more often because of the impact of the down-tilted base station antennas, which result in weakened side lobe signals received at the UAV. As a result of this, sometimes the UAV will receive a stronger signal from more distant base stations than closer ones. This is particularly noticeable at the 100-meter height. Here we see that the neural network is more likely to connect the UAV to the 4th, 5th, or 6th closest base station than it is to the 3rd closest. The neural network has learned approximately how the base station side lobes are distributed at this height above ground, and so will take this into account when choosing the most suitable base station. In conclusion, in this paper we have proposed an intelligent UAV base station association scheme using a neural network. We have demonstrated how this scheme outperforms conventional heuristic association schemes. In our future work, we intend to extend this work to consider a UAV moving through the environment, where handover and mobility effects play a role. Thank you for attending this talk. Please feel free to send any questions to the email provided. This work is co-funded by the National Science Foundation of China and Science Foundation Ireland.